Hi everyone, we are from Group 5. The project that we propose is the food and medicine delivery robot in the hospital, NurseBot.
Coronavirus disease pandemic has been spread globally since the late 2019. It has become a major challenge to the healthcare system across the globe. The frontline medical staff face a higher risk of infection and death due to overexposure to the virus. Technological advancements have contributed limitless assistance to mankind. In this difficult time, the applications of robotics and automation are important in helping the healthcare workers to fight against the infectious disease. Therefore, in this project, we propose to design a dual-arm robot to provide food and medicine for patients suspected or diagnosed with COVID-19 to alternate the nursing services. The robot is known as NurseBot. The ideal role of NurseBot is to take over the repetitive work of the medical staff. The first challenge is lack of manpower. The nursing workforce shortage has caused delay in providing food and medicine to patients. The second challenge is limited access to critical medical supplies such as personal protective equipment, gloves, medical masks, goggles, and etc. The last challenge is practice of social distancing. Practice social distancing can reduce the spread of COVID-19. In addition, the contact of medical staff with patients during the entire treatment process should be minimized. To overcome the challenges faced by healthcare workers, our group decided to design a dual robotic arm robot to deliver food and medicines to patients with suspected or confirmed COVID-19. The robot can perform two important tasks, which are food delivery and medicine delivery. The design model offers infinite turn on the end joint. It is flexible, space-saving, and lightweight. Both robotics arms have 6 degrees of freedom. Left arm is designed to deliver food package with a micro hand gripper. Right arm is designed to deliver medicine to patients with a Jacko hand gripper as an infected. The objectives of this main project are to incorporate robotic arm, which is essential, can be used in hospital for food and medicine delivery purpose, to reduce healthcare workers' workload, to increase the efficiency of food and medicine delivery, and to lower the risk of infection amongst the healthcare workers. To calculate the forward kinematics of the robot, the Navigate Hackathon convention is used. Firstly, draw the kinematic diagram of right robotic arm and assign axes onto each joint. Next, write down the DH parameters for each joint. Each joint transformation is formed by substituting the corresponding DH parameter into the homogeneous transformation matrix. The total transformation of the right arm of the robot is calculated as shown in the slides. The previous procedures are repeated to calculate the forward kinematics of the left robotic arm. Again, each joint transformation is calculated by using the homogeneous transformations matrix. The total transformation of the left arm of the robot is calculated as shown in the slide.
Next, Jacobian of each robotic arm is also being calculated. From previous calculation, which is transformation matrix, the location of each end effector is being calculated. Jacobian represents differential mapping and differential in joint space with Cartesian space by direct differentiation. So this slide shows the Jacobian of right robotic arm. By using the same method, the Jacobian of left robotic arm also being calculated as shown in the slide above. Next, I will share about the component being used for hardware design. Although this NurseBot is not developed in hardware, but these are the components that we propose for hardware design. The first component is BLDC motor driver. Why we choose this motor driver is because of its high performance, multifunctional, low-cost DC brushless driver with a Hall sensor, and it is also flexible. The second component is Arduino Mega. It is a microcontroller to control the dual robotic arm. The third component is proximity sensor. The sensor we chose is stick laser sensor with distance between 0.05 meter and 12 meter. The last component is a brushless motor. It has a high torque to weight ratio and it can help to improve efficiency and also reduce the noise and corrosion.
Hi, I'm Kelvin and now I talk about the methodology. The arm and the NurseBot base was first designed in the CAD software in SolidWorks. So the geometry of the arm were reverse engineered from the UR3 universal arm, including the dimension and the mass property. Next, the URDF of the model was exported. Then, we assembling the URDF in the VREP. The link hierarchy was determined, and the design of the NurseBot was the inspiration from the UR3 dual arm robot, which is shown by the picture in the bottom left of the slide. Next is a control design of the arm in VREP. So once the URDF of the arm were imported into the VREP scene, the joint properties such as the limits were set, the mass, the mode of joint operation, the maximum torque of the motor was also configured. And lastly, the PID controller was implemented in order to produce more desired transient response. Next is the control implementation. So the model was being exported from the SolidWorks to the MATLAB into the Simulink. And then the model was modified so that each joint of the arm can be controlled through the GUI. So the GUI of a joint space controller was created in the app designer in MATLAB. The forward and the inverse kinematic of the algorithm were written in the MATLAB so that the user can interact and observe the arm in real-time simulation. So the configuration of the robot arm was presented in the Sim Mechanic Explorer. Next, I'll talk about the gripper design on the right and left arm. Jack of hand was one of the available gripper in VREP. Due to the cup special geometry, which is the inverted frustum, it requires at least 3 points of contact to grip firmly so that it could provide a better control and consistency during the task. And lastly, the cup was tilted in order to transfer the medication. Next is the left arm. We are using a micro hand for the left arm is because the food package's handle was to be gripped. So the challenge was how we want to orient the end effector in order to place the packages upright along the path. So the trajectory planning comes into the place, which is it was designed in the Cartesian space where the path were defined by a few VR points so that we could have a better control on the path and the end effector poles. Lastly, the damping coefficient were introduced so that we could reduce the oscillation along the path. And finally, this was the flow chart of the whole robot. So the left side of the part was the positioning and the right side of the part was the task performed by the left and right arm simultaneously.
For analysis, trajectory planning is being performed. Trajectory planning assists the end effector to move from point A to B in a certain period of time. It also helps to avoid obstacles and unnecessary strains in joint or actuator. It can be implemented on two kinematic, which is forward and inverse kinematic. In the forward kinematic trajectory planning, the robotic arm is being programmed to start from the home position, which all joint in 0 degree, to the rest position. So for analysis in this kinematic, third joint was rotated to negative 90 degree, while the fifth joint to 45 degree. The characteristic of joint 3 and joint 5 were plotted, as shown in the slide. In inverse trajectory planning, the robotic arm was programmed to move from the rest position to the final position where the transfer of medication takes place. The inverse kinematic joint space trajectory algorithm implements the spline interpolation of 434 trajectory. These two tables showing that the initial and target pose being determined and also the joint angles. 2 fire points also being introduced between the final position and also the initial point. This table shows the polynomial equation of each joint, and there is total 14 boundary condition was computed using MATLAB. From simulation in MATLAB, the characteristic of joint 1, joint 2, and joint 3 is being plotted. Next is showing the characteristic of joint 4, joint 5, and also joint 6.
For VREP simulation, the situation is created to demonstrate the hospital ward for food and medicine delivery purpose. The first screen here is the overall environment of the delivery process, while the second screen is showing the NurseBot following the trajectory path to the desired location. And the third screen is to show the NurseBot is delivering the food and medicine. For robot dynamic analysis, the robot has 6 revolute joints, where its axis of joint 2, 3, and 4 are parallel, and the axis of joint 1 intersect and is normal to the axis of joint 2, and the axis of joint 5 intersect and is normal to the axis of joint 4 and 6. The physical properties shown is mass and central mass, which define from SolidWorks. The table of moment of inertia obtained from SolidWorks are shown as well. The physical properties of the dual robot arm is tabulated. It required for the dynamic analysis calculation by using parameters of mass, center of mass, and initial, which are required for further calculation in MATLAB. The general equation of torque and for joints 1, 2, 3, 4, 5, 6 are shown. The dynamic equation of the 6 DOF robotic arm by finding T is then completed in MATLAB R 2021. The method code and results are extremely long, so they are attached in appendix. In discussion, since the successful development of the robot, the objective in the paper have been achieved. Such food and medicine delivery robot can be one of the larger investment in those for medical workers. The problem of labor shortage in the hospital will be solved, and the physical and psychological pressure of the frontliners will be reduced as well. The robot can be used to reduce the risk of frontliners because it allows frontliners and patients to maintain a better social distance to avoid cross-infection with COVID-19. There are 2 problems faced during processing the simulation design of the food and medicine delivery robot. The first problem is the calculation of the inverse kinematic equation. The kinematic of the UR3 is extremely computationally intensive due to the geometry of the robot arm. The calculation of each joint variable is difficult to determine by manual calculation. The solution proposed to solve the large number of DOF, the MATLAB tools are used to find the solution that could converge to a single final position of the arm. Other than that, the problem that we face is the determination of the cup and foot handle position for the gripper to reach. In the solution proposed, the cup and foot package are positioned at a fixed and known position. During COVID-19 pandemic, energy waste in the hospital has increased in terms of electricity and water. The massive number of patients has both and the demand in high-energy equipment in the hospital for the healthcare purpose. In this paper, the robot have achieved 2 of 17 goals in the United Nations Sustainability Development Goal. The first goal achieved is SDG 11 on sustainable cities and communities. The robot proposed as an enabler for providing food and medicine delivery service in the hospital. It can also underpin low carbon system by efficiently using the resources. The robot can also help in the great valuable renewable energy by enabling smart grids that match the mechatronics devices that are in high demand today and in the future. In addition, this robot also implements SDG 7 on affordable and clean energy. Since there is a high energy requirement and carbon footprint, green growth of ICT technology should be in electricity demand growth in the robotic field. The robot proposed in this paper has matched the demand and the goal to reach renewable energy-based data field. In conclusion, there is some achievement of our project. As a result of VREP simulation, it can move as expected. Both left and right robotic arms are moved in the correct paths. 2 different types of gripper function correctly, which the right gripper is used to deliver food, while the left gripper is used to deliver the medicines. In future work, in order to improve the robustness, operability and feasibility of the robot, a camera module can be installed on each arm. The module can be generated by training robots to recognize the positions of cups and food packaging handles. The position information is written as a Cartesian position relative to the initial reference frame of the arm base, which can be calculated by using the inverse kinematic calculation module. In addition, a LED screen may be installed on the prototype to display animated faces to be more human for the patient. Furthermore, audio component can be installed to allow doctors in the office and patients in the ward to conduct conference calls, which can better maintain social distancing.